Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much, David. So this work that I'm going to be talking today about is work that I mostly did during a summer internship I had last year with that I got to work with Dimitris Achlioptas at MSR Redmond. So in the talk, I'll give a quick introduction to the problem of satisfiability for anybody who isn't already quite familiar with it. Then I'll talk for a very short period about a quick application of a famous algorithm called Belief Propagation to satisfiability. Then I'll talk about another algorithm called Warning Propagation, and I'll apply Belief Propagation to Warning Propagation and talk a little bit about Survey Propagation. So a lot of algorithms with the word propagation. So first of all, I'm going to start by talking about making an omelet. And I see that I have a bug already. There we are. Making an omelet. All right. So I like to make breakfast for myself. And one morning, I looked in my refrigerator and I saw that I had the following ingredients. You can read them. I had bacon, ham, sausage. And I decided to make an omelet, and I decided I wanted to make a particular omelet. In particular, I wanted the omelet to have some sort of meat in it. So I wanted either bacon, ham, or sausage. And I knew that I didn't want both peppers and onions, so I said I want not peppers or not onions in my omelet. Furthermore, if I had bacon, then I wanted to have peppers in my omelet. So I said I wanted to either have not bacon or peppers. And similarly, I wanted to have not ham or onions. And I wanted to know, can I make an omelet with these that satisfies my specification? You have eggs? I hope so. So let's just define the satisfiability problem formally very quickly in terms of omelets. So I start by saying I have a vector x, and let's think of that as specifying which ingredients that I'll put in my omelet. And I'll have a set of clauses, and each clause will be the boolean sum of either variables or their complements. So a clause is relatively easy to satisfy. It's satisfied if any one of the variables or complements is true. A formula is the Boolean product of clauses, and that means that it's satisfied only if all of the clauses are themselves satisfied. And I'll just make a quick note that the formula F is satisfiable to the exact extent that I'm able to still make an omelet. All right. So we can also represent the omelet problem as a certain graph. So here on the left, we have all of our ingredients, and on the right we have all of the constraints that tell us which ingredients we can and can't use together. So this is just a re-encoding of the problem I wrote earlier. And just the thing to note is that if an edge is in blue in color on this graph, then that means that the corresponding variable is not complemented, and if it's red, then the variable is complemented. Yeah. So the first algorithm that probably most people in this room are familiar with is belief propagation. And there's a very simple, straightforward way to apply belief propagation to the omelet problem, and that's to let the variables that we're interested in just be the ingredients that we use in the omelet. And let's define a set of kernels such that each kernel has the value 1 if the problem instance is satisfiable. If a certain solution satisfies the formula, and equal to 0, at least one of the kernels should be equal to 0 if the solution doesn't satisfy the formula. And belief propagation will nicely compute for us a value f of x of each xi, which is approximately equal to the following sum, which you can interpret as an a posteriori probability that each variable takes each value. Okay, so let's get to an example sooner rather than later. This is basically what I just ended up saying on the slide 2 slides ago. So let's apply belief propagation in this way to the omelet problem. So I've put up each of the 5 ingredients and each of the 4 clauses, and I've given them a letter and a number. So if I start off by assuming that the probability of that each variable takes each value with probability 0.5, then I start out with a message going from the clause B from variable B to clause 1, which is a message that's just uniform, 1/2, 1/2. Similarly, from S to 1. Do I have a pointer? I wonder. That would help. Or a laser. Oh, I could use. Oh, that's all right. Oh, okay. Well, thanks. So for the time being, I'll just continue. So, so the messages from B to clause 1, that's these top 2 messages with arrows pointing this way. Those 2 messages take the values 1/2, just because that's the ordinary way to initialize messages. And then let's compute the message going from clause 1 to variable h. So
why does it go in that direction?
Why does it go? So all of the messages go in both directions normally. They do. There is a message from each, defined from each. Oh, thank you very much. So there are messages from each variable to each clause, and they go in both directions. But I'm just computing these particular messages because I can't compute every message. It would just take too long. But computing this message is the likelihood on H. So, yeah. So if H takes the value 0, I've got these switched actually. If H takes the value 0, then the clause is satisfied certainly because H itself satisfies the clause. And if H takes the value 1, or if it takes the value 1, let's say that doesn't satisfy the clause, and so the probability that the clause is satisfied is just 3/4. So this message becomes a likelihood function on this variable h, and you can update the outgoing message, the outgoing probability distribution, by multiplying multiplying the a priori probability distribution by the likelihood function and renormalizing, and you'll end up with that the message from h to variable 4 is these two values, 4/7 and 3/7. So modulo mixing up things a little bit with respect to the signs. This should serve as a kind of example of what belief propagation does if you apply it in this way. Yes. 4/7 and 3. Okay, so a priori the probability on h is I'm saying uniform, so half and half. So I multiply. So that's why I said I actually mixed these up. So I should multiply the probabilities by the likelihood function. So I should get a half times 3/4, that's 3/8. And then a half times 1, that's 4/8. And then I renormalize so that the sum becomes 1, so that's 3/7 and 4/7. Okay? Yes. Exactly, yeah. I'm sorry? Yeah, exactly. The probability that the clause would be satisfied given the value taken by h.
Right, so what's the second number?
We're talking about this message?
Yeah, all the messages have got two
numbers. This message is a message from the variable, and so this message is the probability that the variable takes its value given the information supplied by the clause. So the message from h to 4 is not a message. It is not the probability that the clause is satisfied. It's the probability that the message that variable takes that value. Okay. All right. Yeah, oh yeah. That's the plan. Then we just keep passing messages and so forth. Yeah. It may not settle down ever, but that's the plan. It may not ever converge to anything, but we'll assume for the moment that it does, or we won't. Well, okay. So I'm going to talk about clusters of solutions for a moment. So let's talk about the solutions that exist in a solution space and sort of how they're arranged. So let's just define a cluster as some set of connected solutions, and so that you can't add any more solutions and still have it be all connected. And let's define connected as two solutions are connected if there is a path of adjacent solutions between them. And in this picture, I mean adjacent just to be where there are edges between them. And I forgot to put an edge here, it looks like. But this is supposed to be all a big cluster of solutions. When they're adjacent. In this, okay, wait for one slide. Okay, that's all right. So for the satisfiability problem, we define adjacency as have two solutions with Hamming distance 1, which means that you can go from one solution to the other solution just by flipping one variable. So in the context of satisfiability, that's what we have as adjacency. So just for about 5 minutes, I'm gonna continue the discussion of these clusters on the whiteboard. Oh, okay. this was okay. So suppose we've got some graph specifying a problem, and suppose for the moment that we have a solution that satisfies all of our constraints. So the solution may be 1, 0, 1, 1. And we apply the following procedure. So I look at all of the clauses, and I see, and I look at each variable, and I test to see if I were to put the opposite value of this variable, would all of the clauses still be satisfied? And if all of the clauses still are satisfied, then I replace this 1 by a star. A star means I don't care what the solution is, what the value of this variable is. And then I ignore all of the variables all of the clauses that are attached to this variable, because I say, well, now all of those clauses are able to be satisfied. And I continue, and maybe because this variable takes the value star and this clause is satisfied, maybe now this variable can also be labeled as star. And I go on until I can't repeat the procedure anymore. All of the variables that take values are locally forced to take those values. Now let me call this a pseudocluster, and let me think of the pseudocluster as encompassing all of the solutions that you can get by replacing stars with either 1 or 0. So I'm calling it a pseudocluster, and it's not too hard to convince yourself that a pseudocluster actually is guaranteed to contain the cluster that contains our solution. All right, and furthermore, this cluster will have the property that have the property that if you run a certain algorithm, then the output of that algorithm will be the same label, and the algorithm is the following: for every variable that's set to a 0 or a 1, I'll send out a message, a warning message along each of the edges that are not satisfied, that aren't satisfied by the value that is taken by the variable. So suppose this variable is 1, and this clause is a negated clause, saying that this clause is satisfied only when this variable is 0. So this variable sends out a warning message, w equals 1, which says that this clause is not satisfied by this variable. And for every clause, if all but one of the incoming messages is true, is a warning, then the outgoing message is also a warning. So I have 2 incoming messages that are warnings, suppose, and then the third the outgoing message is a warning. And suppose this message goes to this variable. And finally, after those 2 messages have been defined, I'll define every variable as being a star if it doesn't receive any warning messages, and a 1 if it receives any messages that require it to be 1, and a 0 if it receives any messages that require it to be 0. Now there's also the possibility that it receives two conflicting messages requiring it to be both 1 and 0. And if that's the case, then we know that something went wrong, and this is an invalid pseudocluster. Anyway, if if we run this algorithm and the output of the algorithm is exactly the same as the input algorithm, then let's define that. I just defined a pseudocluster, but I really want to generalize the definition of a pseudocluster to be anything, any assignment that satisfies the condition that when you run this algorithm once, you get back the same thing that you started with, and you can see that that's at least consistent with my previous definition of a pseudocluster. And I apologize for defining things twice, but I want you to think of the second definition that I gave as the real definition of a pseudocluster. All right, so now I think I can go back to yes. Knowing the thing you started with. So a pseudocluster is any assignment of ones, zeros, and stars to your variables, such that if you apply this algorithm, you get back to the same thing that you started with, and there are no contradictions. You need to know what you started with. So you can ask, is this a pseudocluster? And I can tell you, yes, it is, or no, it isn't. So the set of pseudoclusters is all of the set of all assignments that fit that definition. Okay. Yes, because I've only defined one set of messages going from the variables to the clauses, and one set of messages going from the clauses to the variables. So you basically have to compute all of the variable to clause messages first. So yeah, there's no problem with the order in which you calculate the messages. Okay. Yeah. Okay. Great. So, all right. This is the thing that I talked about. So here we have our extended assignment. We define variable to clause warning messages. From those messages, we define clause to variable warning messages, and then we recompute our extended assignment. And let's call that algorithm warning propagation. Right. So formally, it may be worth going through the definition just one more time. The warnings going from a variable x to c. Wait a minute. This is not review. Sorry. This is a different way of stating the warning propagation algorithm in terms not of the stars and ones, but in terms of a hypothetical set of messages from check to variables. So we define the warning from variable to check as being true if any one of the warnings from the checks in C star are true, and C star is just the set of clauses in which the variable appears with opposite sign. And
you're assuming here that x has a particular value at the moment.
So at the moment, I'm not assuming that the variable x has a particular value. I'm assuming that I'm not assuming that. So I'm assuming that the outgoing messages are just a function of the incoming messages now. So the outgoing messages are this function. The variable to check messages are this function, and the the clause to variable messages are true if and only if every variable to clause warning is also true. And so you can also convince yourself that this definition is actually the same as the previous definition if you assume that there are no contradictions at the variable nodes. Okay, C star is just the set of is defined in this picture. You can think of it. The C star is all of the clauses in which the sign, the black clauses, because this is a red. This is because the guy C is connected with the red edge. So this, if this was a black edge, then C star would be all of the red edge clauses. Yeah, sorry about that. And C star star, which I don't use on this slide, but I'll use a little bit later, is all of the other clauses with the same sign. Okay? And X star is all of the variable nodes regardless, all of the other variable nodes regardless of the sign.
So the left-hand picture is saying, let's imagine we want to send out a new message along that particular edge.
Yes.
On the left-hand side. Then what do we need to know? Well, we need to know if any of the black clauses want X to be black.
Yes.
And if
Right.
any of them at all want it to be black,
Right.
then
Then it needs to be black, and therefore that won't be satisfied, and therefore we send a warning to that effect. Yes.
So these W vectors are 0, 1.
Yes. Absolutely.
Taking the sum of them.
Sorry. This. Good. Which sum are you looking at? This one. Yeah. This sum is supposed to be a boolean sum. Yes. Yeah. Maximum. Yeah. Boolean sum is the same as maximum. Yeah. Warning propagation can be viewed as the max product algorithm. Yes, absolutely.
Again, this is an intuitive thing.
Right.
It's not obvious what it does.
It's not. Yeah. It's not. It's not obvious. You can easily construct examples where this doesn't converge to anything. So, which is fine. Right. Fortunately, we're not actually going to apply warning propagation directly. Okay. So I just said that warning propagation, if you want to think of this as an algorithm, you can think of it as terminating in failure if two contradictory messages are received, or terminating in success if a fixed point, if it comes to a fixed point. And by definition, the fixed points of warning propagation are pseudoclusters. So forget the corresponds to. That this is just the definition. That's what pseudoclusters are for now. All right? If we do have a tree, if our problem instance is a tree, or if we restrict ourselves to some subset of a loopy problem that's a tree and fix the boundary conditions, then we know that then it's easy to see that warning propagation converges in some finite number of iterations, actually in no more than the number of iterations that's the diameter of the tree. And there's at most one fixed point, and if there is a fixed point, it corresponds exactly to the actual solution cluster in the sense that if the solution cluster contains all ones, then the pseudo cluster will contain a 1. And if the solution, if the actual cluster contains 1s and 0s, then the pseudo cluster will contain a star in that position. And on a loopy graph, first of all, we're not guaranteed to converge at all. Or if we converge, we can converge. It's easy to have a graph that has many different values that warning propagation can converge to. Furthermore, if you look at any one pseudo cluster, you can, well, in some cases it's going to be in direct correspondence to one particular cluster. It's also possible that the pseudo cluster will contain no clusters, and the way you can convince yourself of that is that you can just take a problem that has so many clauses that you don't expect there to be any solutions, that has, say, all of the clauses have degree at least 3 or even at least 2, then you can easily see that the all stars assignment will be a stable point of the warning propagation algorithm. So there would be a cluster, a pseudo cluster corresponding to that problem, but there may not be any solutions at all, and therefore there would be no clusters. So it can correspond to one cluster, it can correspond to no clusters, and it can also correspond to more than one cluster. So on the other hand, one reason that clusters are that clusters may be a good thing to look for, or in some sense may be good, is that we're guaranteed that the clusters are somewhat far away. You can't just have two clusters that differ only in 1 or 2 positions. In fact, the positions in which 2 clusters disagree on have to be at least as big as an entire loop in the graph. So the central idea of this talk is going to be to apply message passing, apply belief propagation algorithm to, instead of to finding the solutions of our problem, to finding solutions that are fixed points of warning propagation. So in particular, let's let the variables that are the inputs to belief propagation be the set of warnings from X to C and the set of warnings from C to X. And let's let the kernels be some kernels corresponding to X, each variable X, and some kernels corresponding to each clause C. And let's let the kernels take the value 1 when everything is okay and 0 when anything goes wrong. That's the general idea. And specifically, we'll let the kernels be this. So the kernel at the variable X is the product of two things. First of all, the first term is a product that equals to 1 when each of the messages, when each of the outgoing messages are the appropriate functions of the incoming messages. So we have the indicator denoted by I of the equality Wx to C is the sum, the Boolean sum of all x of all C prime and C star of W C prime to X. So this term is going to be 1 when all of the outgoing messages are the appropriate functions of the incoming messages. And furthermore, the second clause, the second factor will be a 1 when there's no conflict in the messages. So you can read the equation for yourself. The first term is going to be 1 when there's some it's going to be 0 when there's some warning from C to X, from C prime to X, anyway, I'm going to get confused. Okay, this is one when there's no conflict. And similarly, if we let the kernels at the check nodes be equal to 1 when the outgoing messages are the appropriate functions of the incoming messages, warning messages. So let's apply belief propagation to warning propagation. And belief propagation is going to define basically 8 sorts of messages. That's variables going from the variables x to the warning message WXC, and the other 8 that you see, the other 7. Now, and some of the messages are written in blue, and some are written in red. You'll notice that the messages that are in red are actually messages that are going in the opposite direction of the warning messages. So this warning message is supposed to be a message from x, from the variable x to the clause c, and we have a message going in the opposite direction, and we'll call those backwards messages, and we'll treat forward messages and backward messages differently. And one thing to note is that the forward messages and the backward messages don't have anything to do with each other, in the sense that the calculation of one never involves the value of the other messages. The forward messages are their own messages, and the backwards messages are their own messages. And so in some sense, this is actually defining 2 separate algorithms, the forward algorithm and the backward algorithm. And for now, I'm just going to talk about the forward algorithm. And the reason why, so now I've only got one message going from X to C, and the reason for that is that the message here was going to be exactly equal to, these 2 messages will be equal because this message will be the product of the incoming messages, and the only incoming message besides the message here is this message. So this message will just be equal to this message, so no problem. So that's called the message X to C, and I've called it the message S for the reason that I want to get you thinking about survey propagation. Now, okay. So if you apply the BP rule at the check nodes, it's not hard to convince or it's possible to convince yourself by just doing the math that the updates will take this form. And the only thing to note is that this update rule is exactly the same as the update rule defined in survey propagation. If you read the papers by Zakina and Bronstein. Similarly, the check node update rules. If you look at the top rule, that's exactly the same as the rule that they define, and it comes out of applying directly pops out when you apply the kernels that I've defined. So the overall picture is the following picture. We have an abstract algorithm called belief propagation, and we can apply it in different ways to the satisfiability problem. The first way, which seems like the more obvious way, is to apply it just to finding the solutions of satisfiability. And if you apply it in this way, then you get what I call naive belief propagation. You can also apply belief propagation to finding the fixed points of warning propagation. And if you do that, and if you follow all of the steps, then it'll turn out that you get exactly survey propagation. And the reason that this is kind of interesting is that, well, people have tried to do this before. People have tried to apply belief propagation to derive survey propagation, but to my knowledge, the only result that is out there, which is also by Bronstein and Zakina and one other author whose name I can't remember right now. What they show is that they can get the same thing, but they don't get the dynamics. They don't get exactly the message passing update. They just can say that the fixed points will be the same. So as far as I know, this is the first derivation of survey propagation that directly applies belief propagation to some kernels. So anyway, yes, please. Yes. No, it doesn't. It doesn't. So you need to use some other algorithm to find an actual solution. It is an easier algorithm. You keep asking the question that's my next slide, which I really like, which I'm really happy about. So the way that you go from one of these algorithms to an actual solution of the problem is basically the following way. You start with your problem instance and you run one of these algorithms. So you run, say, survey propagation, and then you take the output of survey propagation, and based on some heuristic algorithm, you set some of the variables, and you get a simpler problem, and then you do that again until what happens is you can't do that anymore. The reason that you might not ever be able to do that anymore is that it may turn out that the only fixed point of that survey propagation can find is the all stars, or it just assigns 1 to the probability of star everywhere, and so you can't take this route any further. And at which time you can just try applying simpler algorithms. So the algorithm of choice is walkset, which is an algorithm that takes some solution and modifies the solution bit by bit and trying to satisfy each of the clauses in some way. And right. Sorry about that. So the next few slides I'm going to go through quickly. This is just a way of seeing how good a particular solver is. So I define an ensemble with n variables, m clauses, and k literals per clause. So this is just random k-sat. And I can vary over the parameters, but let me fix n and k and characterize the performance of different algorithms based on how often that they can find a solution given this ensemble. So the results are completely hypothetical. Don't look at this at all. I just want to characterize the success of the algorithm as how probable the algorithm is to find a solution given a particular ratio, say, of clauses to variables. So I'm going to skip this. If you want it to,
these ones will always finish within the time budget.
Absolutely. Yeah. So I'm just going to end the talk with a few open questions that I think are interesting. So the first question that I want to pose is, so we defined clusters and we defined pseudoclusters. And we showed that, well, it's not hard to show that for loopy graphs, those concepts are distinct. There may not be exactly the same number of clusters as pseudo-clusters, but it would be interesting to know if on the average, the number of clusters is actually the same or is different from the number of pseudo-clusters or fixed points of warning propagation. Another question is, well, can we actually find at least the number of expected solutions to fixed points of warning propagation by just essentially calculating the probability that any particular say sequence of messages is a solution to warning propagation? And another question is, there was essentially a backwards algorithm that's defined when you write down these kernels, and it would be very interesting to know if the backwards algorithm can be used productively. Is this a different algorithm? I don't know yet. What about this backwards algorithm that falls out of this derivation? And another question is, so what if we want to replace this this kind of clunky procedure by which we set the variables one at a time? Is there some way where we can change the update rules, say, or change something about the algorithm so that it kind of in a smooth way goes from giving us probabilities over distributions over solutions to actually converging to one particular solution? All right. And that's the end of the talk. If you want to see the talk in its present form, you can look here.